Okay, hello to everyone. Good afternoon. It's a pleasure to participate of this conference. I have seen many interesting presentations, so I want to thank to the organization for the invitation. I'm going to talk about the outer edge of the Oort cloud, and as you know, the Oort cloud is a large spherical structure which is around the sun. Could be the remnant of the planetary formation. Sometimes an external perturbation sends object of the cloud through the planetary region, and this is the moment when we can see this object like comets. The inner edge of this structure is between 1,000 and 3,000 astronomical units, and is probably this structure is probably the continuation of the Kuiper belt. However, the outer edge of the Oort cloud is a more complex problem because in this case the cloud is like an edge between two systems, the solar system and the galaxy. And the Milky Way disturb the object of the cloud in several ways. For example, by the gravitational potential or by stellar passage. Some stars close to the sun can have a close approach and produce a distribution of the particles of the cloud. The parameters which define the importance of this phenomena is the rate of encounters. And there are other sources of perturbation, like molecular clouds, but I don't now consider in this study. So, in order to understand how the particles leave the Oort cloud, we perform a three set of numerical simulation, and in each set consider the evolution of a million of particles by 5 gigayears, which is the approximated age of the solar system. And to solve the equation of motion, we use a Boole-Storr integrator. This is a not symplectic integrator. And the potential is included like an analytical model following, like Gianni Tremaine. And this model uses the Hill approximation so that we can define the Jacobi constant and a Jacobi radius, which is similar to the Hill radius of the restrictor three-body problem. Okay, the Jacobi constant can have two parts, a kinetic part and a potential part, which we call effective potential, and has the influence of the sun and the influence of the galaxy. And like in the restrictor three-body problem, we can define zero velocity surface, which are responsible by the existence of forbidden regions. These forbidden regions are very important because can allow us to define limits for the motion of the particles. So we make a simplified analysis and consider the dependence of the Jacobi constant only with the heliocentric distance r. And we represent this in a two-dimensional plot where the heliocentric distance is in the x-axis in logarithmic scale, and the Jacobi constant is in the y-axis. In all the planes, the velocity is considered equal 0, and appear this forbidden region here in blue. And we can see that the forbidden region ends for a critical value of the Jacobi constant. This critical value for the solar system is this here. And below of the critical value, the forbidden region starts close to this value of heliocentric distance, which is the Jacobi radius, which for the solar system has this value here. And these two quantities, the Jacobi radius and the critical value, allow us to define four regions, the regions U1, U2, and U3. These three regions contains unbound particles, particles that are influenced by the galaxy. And the Oort cloud is placed here, where we found bound particles. These particles cannot be able to escape the Oort cloud because of this forbidden region. The importance of this scheme can be appreciated when we consider the last piece in our puzzle, and these are the stellar passage. Some work considers the model of impulse approximation, but we solve the problem by direct integration of an n-body problem. So, what is the importance of a passing star? Well, a passing star is able to change the energy or the Jacobi constant of the particles of the cloud. Then, returning to our scheme, if we consider a particle here, this green star, a bound particle, then one stellar passage will produce a change of the Jacobi constant, a small change of the Jacobi constant of this particle. And several passages will produce a random walk of this particle in the region B. But there were a net effect of increase of the Jacobi constant until the particle crosses the critical value and is now unbound of the sun. And we can compare this behavior, this increase of the energy, with the increase in temperature of heating water. Like a particle eventually cross the critical value and escape, in the water we will have the boiling water, okay? So our results indicate a way for the escape of the particles of the cloud. They have a slow increase of the Jacobi constant until they pass to the region U1, and then the next stellar passage will increase the heliocentric distance and the particles move through the region U2 or the region U3. But where is the edge of the cloud? And to answer this question, we have to see the final distribution of the heliocentric distance R. Here in the gray histogram, we have the final distribution, and the blue histogram is the initial distribution. If we see the two histograms, not see to be an important result because we see a similar final distribution with some particles with large heliocentric distance. However, if we separate the final distribution in the four regions that we define in our scheme, we can see that an important result. Here, the black vertical line indicates the half Jacobi radius, and the red vertical line indicates the quarter part of the Jacobi radius. And we can see here that for larger heliocentric distance, the unbound particles of region U1 are more than the bound particle of region B. And this is very important because this indicates that the influence of the galaxy becomes more important for this larger distance than the gravitational influence of the sun. And so we can consider this like the edge of the Oort cloud, the point where the unstable particles become dominant. But there are another important result. We can see this result if we follow the evolution of the particles in this region U1. Then, here we have the evolution of the density distribution of the heliocentric distance of the particles in the region U1. And the result is surprising. This region will be empty because are populated by unstable particles. However, we found many particles here. And when every stellar passage moves the particles from this region U1 to the other two U regions, at the same time take particles from the Oort cloud and move this stable particle through this region U1 of unstable particles. So this defines a dynamical structure. See that it's not a spatial structure, it's a dynamical structure. And this is populated by, permanently populated by unstable particles. And we call to this population unbound Oort cloud. And we can imagine this structure like a shell of unstable particles around the sun, around the solar system. But more important is that this shell is surrounding the Oort cloud. It's in the external edge of the Oort cloud. You can see the position here at the half Jacobi radius. So if we return to our comparison with the eating water, the boiling water, we can compare the Oort cloud with the boiling water, and the unbound cloud is like the surface of the boiling water. This dynamical structure defines a transition, a region of transition between the solar system and the interstellar space, or between the solar system and the galaxy. And the stellar passage have an important role, and this is they are a source of energy, so that if we have any change in the parameters which define the stellar passage, as for example the rate of encounters, an increase in the rate of encounters, maybe increase the rate of escape of the particle of the cloud, and maybe change the position of the outer edge. However, the structure, the physical structure that we found will be remain. So we will find always this Oort cloud with his unbound Oort cloud around. And to finish, we have found a way in which the particles are able to escape from this Oort cloud. The particles move through the region U1, and then the particles increase the heliocentric distance. Also, we found an outer edge for the Oort cloud, and in this outer edge we found a transition region where there are a population of unstable particles, which we call unbound Oort cloud. This limit, this edge, depends of the encounter rates, and this result is in agreement with the definition of escape radius for white binaries. And my final comment, I hope that in the future could be some observational evidence of this structure that this work is predicting by a theoretical prediction. Okay, and well, this is all. Thanks.
Thank you, Jorge. Very clear. Um, I don't know if somebody have questions. I always the cold nights of observations, 1 for 1 or 2 weeks with Mario Melita, try to detect any passage, and I completely damned. You can measure or which is the fraction of unbound particles in the Oort cloud?
Yes. you can see here the fraction is very low.
Okay.
We have over the 1 million, there are approximately 1,000. So there is
Okay.
0.1% of fraction, very small, really.
Yeah, we
It's
have
difficult
an North
to
cloud
see.
for very time.
Thank you.